molto rapidamente in italiano, il professor è un esperto da anni di queste tecnologie, farà una presentazione di alto livello, per cui niente, mi auguro che sia di vostro interesse.
So, thanks very much. Cesare, thanks very much for the invitation. Pleasure to be here again after 3 years now. And just let me say, it's a pleasure to see how much the community has evolved, to see you guys doing DUE, doing MCR, ALS. So it's water on really to see how much that has evolved. So, what I'm going to try to show in the next half hour is an overview on what we do in the field of volatilomics, which is partially going to be GC-IMS, but you're going to see a couple of other approaches that mix and blend into that whole approach. So hopefully after the end, I'll be able to show that volatilomics is not just hot air. So the focus of today, and I'm sure that you are all aware of what basically that field is covering, is that we are talking about untargeted analysis. So just to put you on the same track, we differentiate between basically targeted, untargeted, and semi-targeted techniques. Semi-targeted just is a mixture of both of the techniques, to just blending the best of the two worlds. But the classical omics approach is untargeted. Now, volatilomics, as those omics, other words, sort of intrinsically come from systems biology. Okay, so the basic idea is that a couple of years ago, when people just moved away from gas chromatography, later realized this was not a good idea, because it was just missing a certain compartment that is not really amenable by classical chromatography techniques. So that means that classical metabolomics approaches were still missing the... Too loud? Okay, I'm too loud. Sorry. Probably I could do that without the microphone. Just so the classical metabolomics approaches typically omit the gas phase, and as you all probably know, it is quite challenging to analyze compounds, high volatile compounds, low boiling compounds by liquid chromatography. They're just gone, right? But the thing is that over the years, the trend has gone too much towards, my opinion, too much towards liquid chromatography techniques. That means challenges that we face is that everything in that field is limited. Hardware platforms, data analysis, software tools, even databases that are available. I mean, what are you guys using when you do GC-IMS NIST, right? That's about it, what is available. So just to give you an idea what we are doing, so we're trying to do complementary approaches in my group, using whatever type of instrument is available and makes sense, and a couple of those are obviously pretty straightforward. What we're doing, maybe that exotic, is that we're hyphenating IMS and mass spectrometry, and we're also hyphenating soft ionization on the GC side, and we're just basically doing whatever type of samples we can get. And meanwhile, I have quite nice cooperations with Italian groups in the field of olive oil and the field of wine, so it's growing. And as you all know, the getting hold of reasonably good and authentic samples is the biggest challenge, mainly apart from the analytical approaches. One special thing that we are also covering is living systems. So if the time permits, I'm going to show a couple of slides of that as well. So GC-IMS is a perfect tool to analyze systems while they are metabolizing, forming metabolites. So fermentation processes, that is. The complementary platform that we have developed over time is a two-tier approach. The first one is the gas phase, the benchtop volatilomics approach, that is mainly described by the prototypes we have. We have two GC-IMS systems, so one injection splits into two detection systems. The most sensitive system we have at the moment is the trapped headspace GC-IMS system, which is a Shimatsu platform with a trapped headspace sampler that freezes after headspace sampling, which increases the sensitivity for the low boilers drastically. And that is subjected into an untargeted workflow, which partially is off the shelf, so MZMine, and partially own software, mainly GC-IMS tools that you probably know from our group. And what I'm going to show in a couple of slides later is that meanwhile we have a no-coding solution for that. So for every one of you who is not too fond to do in Python, that is the good news. That would be the benchtop approach. And on the LC side and the GC soft ionization side, we're using an Orbitrap that is modified by a secret ionization source. So maybe one of you might know that. It's soft ionization for gas chromatography. Going into basically the same workflow, there we do have to use compound discoverer for a couple of reasons. That's not the best solution for me, but we're working on that as well. And meanwhile, we have a GC Orbitrap that is sort of covering that in between. So that helps a lot in doing true metabolomics. Now, the problem with, and that's something I'm probably kicking open doors here, but the thing is that in reality, what you realize is that very often the techniques that you need to solve a problem are not available at the point of care, right? You have the high-end laboratory stuff. We all like those systems, but you will never get them to where you need them. I believe a couple of people from customs are here, so this is obviously clear. You can't do high-end analysis at customs. So the question is how much, how possible or how easy, feasible it is to transfer analytical knowledge that has been developed in high-end laboratory approaches, NMR spectroscopy, high-end mass spectrometry, so all those systems that need high infrastructure demands. How well is it possible to translate that down to point of care analysis? And to translate that, to translate that to volatilomics, I mean, one of the nice platforms that we're working with, that Thomas supplied us with, is the FlavorSpec 25 at the moment, so which is really a promising approach to translate high-end information to the point of need. And this is a very simple example, but that shows how powerful that approach could be. That's just grapefruit juice from a project that we had, white grapefruit juice in a high fresh quality, so deep frozen after production. And the other one is slightly fermented. You can easily see those ester formations that's quite typical for fermentations. So one of the things, and this is something you all are probably aware, or at least most of you are aware, is that what we're generating here is highly complex data, because you have the GC domain and you have the ion mobility domain, which perfectly pair up, since the gas chromatography separation happens in the second to minute base, and the ion mobility happens in the millisecond base. So this is close to GC-IMS data, with the really, really important advantage that typically you do not need pre-enrichment. And this is something you have to keep in mind. This is of utmost value, because you don't change anything and you don't have absorption-desorption effects that completely change the picture. The problem, obviously, is, or the limitation, when there's light and shadow, you do not get the mass to charge information. And that's why we do this additional approach with mass spectrometry. Just by interest, how many people of you have a GC-IMS MS system running? One. Okay, good. So hopefully next 3 years, a couple more. This is really, it's not perfect, but it's really, really a nice approach, because you combine more or less the best of two worlds. More or less means electron ionization is not the best of the two worlds, right? Because you have a hard ionization, so it's limited to a certain point of compounds. Terpenes are not best thing. I'd probably tell that something that is known, but it is at least an approach that allows you to go to versus databases. This is really, really valuable. Now, again, the problem with that is you need software, right? Unless you don't want to use 3 platforms for data analysis here, data analysis there, then migrating the data and so on, this is completely tedious. And that's what we realized over time. So we started developing our own tool set, software platform, which is GC-IMS. And just to give you an idea, again, again, that is kicking open doors, but you have to realize that the data you are generating is extremely high dimensional. And if you add something like mass spectrometry as an additional dimension, this is additional high dimension. And what we have to do with that data, you have to reduce the data, right? Because it's highly collinear, highly covariant. And if you want to do things like a regression, so you just saw MCR parafact. This is basically all the same strategy. You're deconvoluting, or you're reducing dimensionality in order to avoid that high dimensionality effect. Now, there's a plethora of different tools that you can use for reducing dimensionality. You can use a plethora of different tools for doing feature selection. I also saw the term features are a very important thing. You will realize that the data is too complex for just doing full fingerprint data in a lot of cases. So you don't get discouraged if the separation doesn't work in the first instance. Try feature selection. That is very often a very good way to go. And this is one of my last slides that really goes too much into detail on the data science side, because I wanted to spare you guys from diving too deep into that. And this is actually one of the few times I talk about AI, because lots of the stuff, or most of the stuff that we do is not AI, right? It's machine learning, it's neural networks, but it's not AI. Not in a way that you would consider AI in forms of a generative system or an agent system. I'm sure there are going to be approaches. We're working on LLMs also in that field, but this is completely at the basis at the moment. So this is just a very simple example of what you can do with a reasonable strategy when you generate data, like you did a lot of PCA, you did also PCA, you did MCR, and all of that data can be backwards projected into the original data space. And the interesting thing about that sounds complex, but the interesting idea behind that is that you get the original data space, retention time and drift time, with the information that comes from data analysis. So you now see exactly in the original data space what happens with your data. And as I started teasing, is that we developed we're still in the process of developing a non-coding solution that is called GC-IMS. And for those people of you who are using IMS only, works fairly well as well, but the principal idea is the mapping of the mass spectrometry data to the IMS data or vice versa. Okay, and the interesting thing is that you can connect that data with NIST data, and what you can just see here is hopefully that works, a video of just a ketone standard, so that's nothing special, it's just a reference standard you can select. You see that here we have the mapping of the IMS and the MS signals. You just select the peak of interest, get the mass spectrum, NIST church, and that's it. Okay? So this is still fundamental, in a fundamental stage. We're not doing a reasonable deconvolution. We're planning at the moment to do MCR deconvolution on the mass spec side, but this is a tool that really helps a lot in speeding up processes and really making the best use out of the data. So if you don't have a GC-IMS MS system, but you have an IMS system and an MS system, think about merging those systems together. It's really worthwhile. So, application examples. First one I really like is citrus peel oils, because citrus peel oils are extremely complex in their composition. It's amazing how much difference you have in those oils, and depending on the production type, in terms of quality and so on. And this is actually from a PhD student of mine from Lucas. He developed that approach, and this is a chiral trapped headspace analysis. And also very important for you guys, and I'm sure you know that, nearly everything that happens in nature is chiral. And this is something very often is not considered as an important feature. And if you think about using that information for data analysis, that's a treasure, right? Because you have, depending on geographies, on temperatures, on cultivars, whatever, you will see differences in the enantiomeric distribution. These are features that you can use, right? And so far, most of the approaches don't use that. So again, this is the trapped headspace system. And what you can see here is a chiral, off-the-shelf BGB column, so nothing special. And just an example for bitter orange and sweet orange. Yes, that's completely different, obviously. But just to show, for the sake of simplicity, to show how well that works, that you get the enantiomeric distribution quite well in that column. And obviously, the enantiomers do not separate in the IMS phase, at least not in our systems. There are approaches that discuss that. I'm not so sure that really works, but at those systems, you do not have a separation in the IMS stage, but you have a separation in the retention time. Another thing, and I'm just making advertisements here again, I mean, every one of you is afflicted by the Iran war and increasing prices for helium, and everything goes up in prices. So hydrogen does have a revival in a way, and it's so important to realize how much potential is in using hydrogen. It's an old stuff. I mean, it's really old stuff, but it's coming up again. And just to show that it's not peel oils. That's cocoa liquor. We did another project with Little Spot, German chocolate company, the quadratic ones. And you see, this is roughly 1,500 seconds here in nitrogen, and this is just 500 or 600 seconds with hydrogen. So we can easily go up to 2.4. We even did analysis with 150 centimeters per second and still got a reasonable separation. Why? Because the Van Diemen's function is so flat. So it's even possible to do chiral analysis. We did chiral analysis in 10 minutes, baseline separated. It's amazing. And why? Because GC-IMS is extremely tolerant towards hydrogen. Mass spec is not yet. We're working with Shimatsu and doing a prototype ion source, which probably might be the solution for exactly that problem. I mean, imagine if you can do separation in 10 minutes with full chiral separation. So how good can it get, right? Now, looking at these data from these peel oils, frequently when I show that in Congress, is one of the questions always, couldn't you have analyzed more samples? No, this is by far one of the biggest authentic peel oil sample sets that I've found in the market, because we're working with a company specialized in that. And so this works quite well, right? So you see the confusion matrix. So I'm quite happy with that. We have one misplacement for the mandarin peel oil. That's these two, by the way. And this is not an error. These are red mandarin peel oils. Before that, I didn't even know that this exists, but this is a specific type of very expensive mandarin peel oil, and that separates. Now, again, why do they separate? You know, it's always nice to have those correlations, but the important question is, what's the causality behind that, right? And that's where really GC-IMS is proficient. And what you see here is just a really simple PCA analysis of those peel oils, and the separation between Tahiti and key lime is pretty easy. That's quite straightforward. That's not much of a challenge. What is much more interesting, that we're even able to differentiate within the key limes between type A and type B. And type A is the type that is obtained by juice oil emulsion production. You just squeeze the whole fruit. And the type B is just, you scrape off the skin as you would do it at home. That's much more expensive, but the quality is higher. The thing is that, so these are Persian lime and key lime. The question is, why do those differentiate, right? And if you look at the backwards projection of into the PCA again, what you basically can see is that the blue signal, or the blue color, means less abundant type B, and red one would mean more abundant type B. So that's basically a transport of the information into backward projection. So what you can see is that these signals are less abundant in type B, so type B is a higher quality. So it might be likely that these are oxidation products. And since we have the GC-IMS approach, we can just backwards project that to the mass spectrometry data and look at the information. So this was still done manually. This is not done by GC-IMS yet. That would deliver exactly the same result. But what you can see here is, it makes sense from a chemical point of view, that we have oxidation artifacts like the sulcatone, which is a typical oxidation artifact of the isoprenic pathway intermediates, and the terpineol is well known for being an artifact for concentrate juices. So this is quite interesting to see that in a data-driven approach, because we didn't explicitly search for that. Why does it make sense to use GC-IMS here? Because in a non-targeted approach, we wouldn't have found it, because the intensity is so low that we even had to enrich that in a trap sample 5 times, because we're just doing headspace. We're not doing a liquid injection, okay? So another example that I really like, because this is a very recent project, and I'm going to a bit more in detail, so I hope you forgive me if it's a bit more detailed here. The principal idea behind that project, or projects, it's 3 meanwhile, because coffee just hit as like a train, lots of ideas, and we just dived into deeper and realized there's so much potential in there. Controlled fermentation, I'm going to show what I mean with that, is a specific type of pre-treatment of the coffee cherries. You know that coffee typically is wild type fermented, so spontaneous fermented. You just leave that, depending on how the coffee is produced, you leave that on crates or even on the ground. So that fermentation is mainly defined by the microbiota that are present there. That might be good, but it could be as well not be good. So the stability of the flavor of the aroma might be differing. And depending on the production conditions and the size of the manufacturers, that leaves you with a high variance in the quality. Together with a cooperation partner in Mannheim, Dr. Steffen Schwarz, he's an expert in sensory. We did that project on the side of the growers in Brazil and in India, followed by precise roasting and the sensory evaluation. And then that was our part here. We did a multi-omics approach on the GC high resolution side, on the GC-IMS side, on the GC-IMS side, plus LC-MS side. I'm not going to show the high resolution LC data today. We're going to stick to the volatilomics part, obviously, and then followed by a machine learning, deep learning, whatever you can imagine. Okay, so basically all the tools that you can imagine in that field are part of that project, with the idea to, that is a very high level thing, to try to match patterns to sensory perception. I know this is sort of the holy grail in sensory, and lots of people from flavor experts say that won't work, but the idea is principally, can we predict flavor or the flavor profile by looking at the pattern? And for that, again, GC-IMS is a perfect tool. Other than that, off-flavor screening, again, this is something that is pretty problematic when the stability of the coffee in production varies a lot. So, and this is really something I'm quite proud of, because the sample set speaks for itself. We have a lot of samples, because I sent one of my PhD students for 2 weeks' time to Brazil, and she did the samples by herself. So I know these samples are genuine. And we used 2 different Arabica varieties, Catuai Vermelho and Amarelo, so the red and the yellow Catuai, which differ phenomenologically by that the yellow one has, let's say, less compounds. This is quite interesting also for yeast fermentation. Typically, all of those were biological replicates in a way that these were fermented separately. Biological replicates a bit in abbreviation marks, because it wasn't exactly from the same tree, 30 times repeated. It was a blend from different trees, obviously, but from the same exact region. So quite a lot. So why, may I ask, why 10 only for that one? Because 20 of them were just moldy. So that was a problem we had in that context. Okay, so this is how that looked like. Actually, we did a lot of more than what I'm going to show here. So we had harvested greens, semi-ripes, and ripe. I'm only going to show the results for the ripes today, which ended after the fermentation after 2 days. So that was a small batch fermentation of 5 liters with 2 kilograms of cherries each. Up to 4 days of fermentation, you can see that just really there's a lot of fermentation here, because those ripe cherries contain a lot of sugar. Just looking at a watch. And then the rest of the process is the same. So we did depulping, washing, all that stuff that happens afterwards. Now this is the workflow for the volatilomics approach that we use. So we had a standardized procedure for preparing the coffee samples, ground or milled, and with liquid nitrogen. This is the roast coffee, what I'm showing today only. We also did the same with the green coffee. On the IMS side, that was done on the flavor spec. And then towards easy IMS or towards Vocal, the GS software, in particular for the annotation, just to get an idea on how well that performs versus the mass spectrometry data. Okay. The other strategies were obviously the mass spec based, or the hyphenated mass spec IMS based. And again, here we're just combining the data from those 2 sources, where you just had to realize that the quality, even though metabolomics work quite well with unit resolution data, so GC-IMS based data, so just quadruple data works quite well for doing metabolomics. The hit rate in databases, or the annotation quality in databases, is substantially higher if you have high-res data. That's the way it is. Since last year, we combined those workflows from the data analysis software platforms, basically, to MetaboAnalyst. I'm meanwhile a big fan. I'm not sure whether some guys are using MetaboAnalyst, so I would recommend that, because it's extremely powerful in terms of having a broad coverage of tools available in a standardized format for all types of data from NMR spectroscopy to mass spectrometry, so it works quite well. And looking at those data, this is from Nico. Nikolai, he sits at the back. He was guest researcher for a couple of months in my group, so he did all that analysis. Plenty of samples prepared. So my compliments. And what you can see here, and this is just a simple PLSDA. I forgot to show you. It's a simple PLSDA, and I spared you from the numbers. So forgive me for all of you who are more deep in data analysis. This is a multi-class problem. So for all of you who are a bit more into detail, this is a multi-class problem. I usually wouldn't do that, okay? So because it's not really necessary to separate between the cultivars and the type of fermentation, that doesn't make sense in that context. I would use normally a different algorithm, but that really shows quite well how proficient that approach is. What we can relatively well differentiate is the different K2IEs the CA and CV. And what is much more interesting is that you can differentiate the wild type fermentation versus the directed fermentation, the controlled fermentation. And this is interesting in context because if you plan to produce a high level quality of coffee by this controlled fermentation, you would want to have a proof or be able to prove, give a proof that this is indeed controlled fermentation coffee, unless you want to go into some molecular biological approaches, which in roast coffee, I'm not so sure whether that's going to work. So that could be an option for point of care analysis. Now, just to dive on the side, what you can do with that data, if you hit that into the Orbitrap, this is obviously much more information, right? That's not a fair comparison because it's a completely different type of data that comes out of those systems. And you can see that obviously the wild type behaves differently than the rest of the controlled fermentations, which probably is related to the fact that we have a mixed microbiota in the wild fermentation, and the yeast and the controlled fermentation just overgrow the rest of the fermentation. But what's really nice is you can get those heat maps. You can identify potential metabolites, and the idea that we're following is to map that back to the information of the IMS. So just that you can just put that system back to the producer or the cooperative that might be buying such a system. And also, I just heard biomarker search in the last talks. This is something that really works also well with OPLSDA, for example, right? So you can do that in the SPLOT, or this is a VIP score filtering. That's also quite nice for feature selection. Okay, and for the last couple of minutes, what I'm going to show, this is completely outside of the food realm. We're also doing biotechnology a lot, and that's what we call online omics or fermentomics. I'm aware this term has been taken already, but I'm just using. Come again? Fermentomics. I think that term is already taken, but I just use that, reuse that. Now, this is from a project that we did last year with BASF, and with a prototype that Thomas supplied us with. So this is an industrial system for GC-IMS that is suitable for being used in a production environment. You guys had a lot of trouble refitting that for those standards for BASF, so it was ridiculous. Anyways, so we're doing the same thing, but the idea of that fermentation analysis is that we're doing a real-time monitoring of the fermentation without breaking the sterile barrier, right? The thing is that normally you take samples from the fermentation or from a cell culture, by the way, it works the same. Here we just take the exhaust air because that is there anyway, right? All of those fermentations are being aerated, so you have a lot of off-gas stream, and we're using that. And what you can see here is a fermentation running in real time, so 5-minute steps, of a licheniformis fermentation. And what is quite fascinating is that in comparison to what you would get with Raman or with infrared spectroscopy, you can differentiate on a molecular species level. This is fascinating because you can see that compounds are being formed, being degraded again. And if you see that, this is so much potential in optimizing and understanding fermentations in a better way than typically today biotechnologists do. Because now that's prerogative, but biotechnology is like, in a way, low tech, because people say, oh, I have oxygen, I have carbon dioxide, the process looks all the time, it's good to go. And this is not doing that in an optimal way, right? And if you look at what you can do with that data now, you can model, you can do all the fancy stuff with that. You can do machine learning. This is a support vector regression, so a non-linear regression of batch maturity, so predicted time versus real time. So after a couple of runs, we can predict for that specific fermentation time at what time it would be mature to harvest or stop or whatever you would do with that fermentation. You could quantitate compounds in real time in the gas phase. I mean, this is completely hilarious. You can just select a couple of compounds that might be relevant for your fermentation quality rating. You can say, okay, now for this terpene of interest, now is the time to harvest. Okay, not just wait longer until you have apoptosis or whatever that might happen. So this is really fascinating. What we realize is that peak annotation is quite challenging. And so last slide. What we're doing currently is a new project that Thomas is building as a prototype at the moment. It's an 8-port stream selector that is basically an IMS with an automated stream selecting system that allows us to add that to a shake flask incubator or to a reaction system. So you have multiple reactors. We can do that at the same time, repetitively, generating a lot of data. And this is fit for doing deep learning. This is fit for really doing AI type of approaches because you can generate so much data. When you do that with these 2-3 days fermentation time, you generate a massive amount of data with a high variance of exactly what neural networks will need. With that, I thank you for your attention. Thanks for my cooperation partners. And last but not least, if you were interested in testing or doing better tests, feel free to download both of the software. So thanks very much.